science has to bend a little to make the plot of a movie work better, and we don't want to criticize those choices, but we do want to make fun of them. Failed physics, up next on Science Goes to the Movies. Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Lisa Beth Kovetz. On this episode, we're going to look at some of the most consistent ways movies break the laws of physics. I'm joined today by two of our favorite physicists. Professor Vinod Menon of CCNY researches light matter interactions on the nanoscale. Matt O'Dowd, host of PBS Spacetime and Lehman College professor of astrophysics, works on the galactic scale. Welcome back to the show.
Thank you.
Thank you, Lisa. It's good to be here.
Yeah, great to be here back.
When villains started dropping girlfriends, and it's always the girlfriends, from higher and higher heights, that wasn't a problem for superheroes. They just flew in, caught the girl, and everything was great. But if Professor Matt O'Dowd was a supervillain determined to take over CUNY TV, and he dragged the whole lot of us across the street and started tossing camera operators off the top of the Empire State Building, would it help any of us at all if Professor Vinod Menon flew in and caught us as we fell?
I think it should.
Well, so, given that Captain Professor Vinod Menon is a physicist, he'd probably know how to do it right. I think, so movie superheroes who have not taken advanced physics, they fail at one point, which is that if you stop someone falling suddenly with your arms of steel, it's about as good as stopping suddenly when you hit the deck. So
is there a way to use physics to appropriately save someone, Captain?
Yeah, so
Captain
you need
Physics?
to continue. It's like jumping off a moving bus.
you know,
Haven't you done?
Okay, so the last time I jumped off a moving bus, last time I rode my bike and tried to stop, I fell. And I skinned my knees. So how would you
So
do
you
that?
need to run along with the bus as you jump off the bus. So you just need to keep that motion going. So when you're catching somebody, you need to make sure that you do it in such a way that you're continuing the person's motion and is not jerking it in.
So when supervillain Matt throws our director Catalan off the top of the Empire State Building, you're going to continue going down as you catch him. You're going to slow him.
right.
Yeah.
It's the impulse that kills
Yes.
you. The delta momentum, the change in momentum that kills you. It's not whether it's concrete or arms of steel.
Exactly.
Our guest, Matt O'Dowd, started to tell me once that superhero super strength bugs him because it breaks conservation of momentum. But then he stopped and said that was just true nerd rage and not justifiable, but I like true nerd rage. And I want to know, why does super strength break the conservation of momentum?
Okay, you're ready to let out the beast. That's the problem with becoming a physicist. It just ruins movies for you.
Yes, exactly.
Well, there are two things really. So, if Superman can stand there and stop a locomotive or a truck with just his sheer strength, okay, that's one thing. Maybe he is that strong, but he doesn't weigh as much as a truck or a locomotive, and so regardless of how much physical strength he has, he's going to move with whatever he impacts. If he tries to fly up and catch an asteroid, his only capacity to resist that asteroid is his speed plus his mass. Okay, so that's his momentum, speed plus mass. And so if he's pushing that squillion-ton asteroid back into space, then he's breaking what we call the law of conservation of momentum. What should really happen is that the asteroid collects him and continues on its way back to Earth. Which puts me in mind of another problem, which is that when any of these superheroes fly, and we see them fly through space, they don't eject any propellant behind them, right? So if you're in space and you don't have any propellant, no matter how strong you are, then you just hang there in space.
Right. You can't kick your legs.
You can't kick your legs in space.
But I think that it may be super nerd rage, but there's certain expectations that get built around seeing things in movies happen, and when these tropes form, again, an expectation that this is what the world is. So I think it is important to sort of say, no, there are laws of physics and they're not suggestions of physics.
Yeah. Well, I don't think superhero movies are science fiction. They're fantastical. So Superman flies by magic. The Incredible Hulk, on the other hand, flies by jumping really high, and that is by comparison very reasonable. Douglas Adams had a nice line, I guess it was in one of the Hitchhikers, like one of the latter Hitchhikers books, which is that the secret to flying is throwing yourself at the ground and missing. So there you go.
Yeah.
When we see the Enterprise or the Millennium Falcon or the Orville enter an asteroid belt, usually to hide from the Empire or killer aliens, those huge rocks move like a giant herd of helium balloons. But they're huge rocks, and they're really close to each other. Has gravity abandoned an asteroid belt? Do the rocks no longer?
So there are so many issues here. You know, I'm a Star Wars fan, so I hate to burst this bubble, so to speak. But so certainly they would interact gravitationally. They're quite small, so asteroids, you know, a typical size might be a meter or two, plus a lot of grains. The really big ones are quite rare. So although they do interact gravitationally, it's weak. So it's a weak, and it takes a very long time for them to slowly move together and congregate. And you know, it would take, you know, presumably millions of years for them to, for example, congregate and start to form something that might become a planet. Okay, that's how we think the planet Earth formed, from just the gravitational congregation of a much, much denser asteroid belt. Now, the asteroid belt that we see in movies is typically rocks all over the place. For reference, the rough density of our own asteroid belt, the one between Mars and Jupiter, something like 200 kilometers between asteroids on average. So it's mostly empty space.
Yeah.
Yeah, and so that's the main reason that they're not going to be smashing into each other too often.
So asteroid belts are or are not made up of something, made up of rocks big enough to hide the Orville or big enough to hide the Millennium Falcon?
There are definitely some in the asteroid belt that would be big enough, but things that are represented in those movies they're rare in asteroid belts. The main thing is when you could fly through an asteroid belt, and you probably wouldn't have to steer in order to miss everything.
Oh, because it's so large. It's not that
Because it's mostly empty space. Yeah.
That is not visually exciting.
It's not visually exciting. Yes. Yeah. Astrophysically accurate movies are extremely boring.
You would see one go by and then you would have to wait another 5 minutes before the next one. Yeah.
No, that's bad cinematography. Yes. In the movies, there's, you know, tons and tons and tons of habitable planets. Is that valid? Are there tons and tons of habitable planets?
Yes, but our definition of habitable is not as generous as some people's definition of habitable. There are tons of planets that are presumably roughly Earth-sized, okay, within, you know, a small margin, and which are the right distance from their star to have liquid water. So this is essentially the definition of habitability for an astronomer. Oh. Habitable, having a nice, you know, oxygen-rich atmosphere and Starbucks in every corner, and that we do not know yet.
And it's not clear that we need oxygen for some other form of species that might evolve in some other.
There was life on Earth before there was oxygen in the atmosphere.
Yes.
In the middle of a battle, when your science officer informs you that the enemy has locked their photon torpedoes on your ship, of course, the next thing you do is instruct your helmsman to prepare evasive maneuvers. But light moves fast. How far away would you have to be to evade a light-based weapon?
Okay, so I think firstly, the photon torpedo is not essentially a particle of light coming in. It's actually got an antimatter-matter chamber separated. And then it's the collision of the antimatter and matter that actually creates the light to come out.
How do you know this?
Well, I'm gonna
How do you not know this, Matt?
Were you part of the research team?
That's fascinating.
So, or at least that's my understanding of how the photon torpedo works. But the problem that in realizing that is it's not easy to confine antimatter. So, so there's some practical issues there of how to do this. Now, going back to your question of whether if
Wait, so why would they call it a photon torpedo then?
because at the end, so when it explodes, it's actually light that comes out because you're combining, it's energy that gets released because it's a matter antimatter shaking hands, and then it just creates this huge blast of light that comes out.
That would be a way bigger explosion though than what we see.
You could create a lot of energy out of that.
Yeah.
Absolutely.
I'm sorry, go ahead.
Yes. So, but talking about if it was a light-based weapon that was being used, then light travels at 3 times 10 to the 8th meters per second. That's 3 followed by 8 zeros, and that just to get an idea, light typically takes about I think 65 milliseconds to go halfway around the Earth. Okay, and then another 65 to go around. So, and that's typically the reaction time for human beings is about 0.25 seconds. So if you put that, that's about 250 milliseconds. Let's say you have superpowers and you're better off, so half that, so 125. So the time it takes for light to go around one circle would roughly be the reaction time you have to make a maneuver. So if it was a pure light-based system and somehow you knew that was locked onto you, because remember, information also cannot travel faster than light. So hypothetically, if you knew that somebody had locked this on you, then you would have about 125 milliseconds to react if you were at a distance that's equal to the circumference of the Earth.
By the time I said stick 'em up,
Yes.
you'd be
Yeah.
the light would already
Light would be
a long time.
unless you're really far away, then you have some.
Right. Well, can light even be weaponized? I mean, we see light weapons are fabulous cinematography. They look so great, but can
Yes, absolutely. Light, so the whole Star Wars program that the U.S. had was a good example of light-based weapons that they wanted to build. And more recently, there are laser-based weapons that have been built to shoot down things. If you just think about it, I mean, you can, forget weapons. I'd rather look at some place where the same energy is used for something good. So laser eye surgery is an example where you're burning a part of your tissue. And so laser, just by using light, you can, as long as you can focus it down to tiny regions, you can actually burn certain parts of your tissue. And that's how it works. So the same idea of imparting a huge amount of energy in a small region, and the photons all have the same property, they're coherent, makes them really
with incredible exactitude because they're so small.
Exactly. Yep.
And does light is the separation of matter and antimatter the only way to make light explode?
Well, in the photon torpedo, that is the concept. But if you want to generate light, I mean, there are other ways you can generate light. Like you can smash particles together, and they would produce light. Where you essentially release of energy, right? I mean, so when we think about light, we always think about light as what we see.
Yeah.
But light actually is electromagnetic radiation that goes all the way from radio waves, which we use for cell phones and so on, and microwaves, to gamma rays and X-rays, which are all the way in the other part of the electromagnetic spectrum. And all of them behave differently to matter. So you can, for example, receive cell phone signal inside a building, although the towers are outside, whereas you can't see the tower.
Let's talk about the high-tech heist. The high-tech heist is a really fun movie trope, and the last layer of techno-protection surrounding the diamond or the hard drive or the general MacGuffin is often a spider web of crisscrossing laser beams that the hero or villain must first spray something on in order to detect. Can we do that? Can filling the air with particles make these invisible rays of light visible?
Yes. So in fact, that's usually how we shoot photographs in our lab. Because if you want to see the laser beams bounce back and forth, you need something for the light to scatter off. And so these particles that we are spraying or whatnot, light is getting scattered off that thing, and that's why we are seeing it. So for example, in my lab, we would use a smoke machine. And then you can see the laser beams going through.
Is this your lab
Right.
that we have on
Well,
the?
something like that, except we'll be wearing glasses if you were inside. Yeah, so you could make the laser beams visible.
So 1 point for the movies, they have got that right.
Well, except for the fact that then when you're looking at a fictional fight in space, like a starship battle,
Yes.
the lasers are always visible in space.
Exactly.
And they shouldn't be unless someone was out there with a smoke machine.
Smoke machine, exactly. So you need something for the light to scatter off. Otherwise, you don't see,
Yeah.
And there's absolutely nothing.
Unless you were at the wrong end of that.
Yes.
In
Yeah.
which case,
If you're on the receiving end.
yeah, you would
If
see
you're on
it
the receiving
momentarily.
end, you would see
You'd
it coming at you.
very briefly. Well, you would see it when it hit you. Very briefly.
What was that?
Yeah. You would just punch. It'll be a tiny small hole
Right.
in your. Yeah.
I want to show you one of my absolutely favorite moments from season 2 of The Flash.
Okay, son, make me proud. Like I care. Now what?
So,
Wasn't that Prison Break? All right.
well, along with the idea that Captain Cold has absolutely zero daddy issues, what is impossible about that sequence?
Take it away. Take it away.
So the fact that he's able to freeze light is definitely a problem there. That it's completely turns into ice, and then he's just able to walk through it. Which, because light is actually, wave. If you think of it as waves, then there's a way you're freezing the light. Having said that, I must point out that people have been able to stop light, but you need a medium or some atomic medium in which you have a set of laser beams that you shine, and then what you do essentially is you slow down the light inside that medium so much that it almost becomes standstill, and then you can release it later. So the concept of freezing light, if I don't want to use the word freezing light, I would use it more as stopping light, is possible.
But not temperature based.
But it's not, not
Yeah,
temperature
and
based.
certainly not turn it into a physical
That's-
breakable
Exactly.
substance.
In fact, what would happen is as soon as he turned that off, if it was a real thing, then the laser beam should come back on.
Right.
So he can't just turn it on, freeze it, and then walk through it. So that's
Is there an explosion if you stop light and then
no. It would come back. The laser
It
would.
just comes back
It'll just turn on back.
just turn back on? So, but it's interesting because you both work with light in different ways. So, a question for both of you: is light made up of something different than everything else in our universe?
Well, yes, sure. I mean, it's its own very unique thing. It's as Vinod said, it's a wave in it's an electromagnetic wave, which is a wave in kind of the field that it itself is one of the fundamental forces of our universe. So electromagnetism itself is a force, but it is a field in which you can have these waves that manifest as photons. And it's one of the weirdest things in the world, really. It's really the first stuff in which we realized the quantum weirdness of reality, when we started to analyze the behavior of light. Way back in the 1700s, the Young two-slit experiment, seeing how, this simple everyday stuff, the sunlight on your face, had this bizarre property under certain experiments that ultimately was the window to all of quantum mechanics. So light behaves extremely weirdly. And it turns out that everything does, but light has the most kind of manifest quantum weirdness.
Does it have its own?
And also the fact that it's the fastest thing that we know, and
The fastest thing in our world.
yes.
Is it?
Well, every few years somebody will claim that they've got something faster than light, and then it gets debunked.
Yeah.
And information itself cannot travel faster than light. And as Matt rightly pointed out, now a lot of the quantum ideas that emerged in the early 1900s and mid 1900s are now becoming technologies using the idea of the quantum property of light. Yeah.
Mhm. Yeah, and so I mean, I guess the big thing about light is that a so-called particle of light, a photon, has no mass, and there aren't many things that we experience directly that have that property of having no mass.
Why is that so remarkable that something has no mass?
Well, for one thing, it's what allows light to be the fastest thing that there is. So the having of mass is what slows us down, as you'll know after a heavy meal. But
Yeah.
light, yeah. So and it as well as opening the door to all of quantum theory, in a sense, it also opened the door to all of Einstein's relativity,
Yes.
because the realization that that light, this massless stuff, travels at the fastest speed there is, and also the fact that that speed of light is experienced in the same way by anybody, no matter what their own speed is. It's itself a truly bizarre and unintuitive thing. You could be Superman traveling at 90% the speed of light, chasing down a photon, but it would still appear to be traveling at the speed of light. Anyway, a couple of minor mathematical flurries from there gave us the theory of special relativity.
Also, Matt, light of various parts of the electromagnetic spectrum is what has helped people see what's out there in the outer universe.
Oh, astronomy.
Yeah, astronomy.
Astronomy,
Yes.
yes. It's almost everything we know
Yeah.
about the universe beyond, our atmosphere comes
Yes.
from light.
Yeah.
We've only just learned to detect gravitational waves, so we're going to get more information. But light has given us
Yes.
our view of the universe.
Exactly.
There's a terribly sad issue that I feel we have to discuss. In all of our best sci-fi space operas, all of the ships travel faster than the speed of light. Can we have that someday, please, guys? Could you get that for us?
Like I was just saying, it's the fastest thing that we know, and there have
But-
been people proposing ideas of how this could travel. There could be particles traveling faster, but theoretically there have been some proposals, but experimentally there's
Well, there's quantum tunneling.
yes.
So experimentalists have managed to teleport light over short distance, laboratory scale distances, but that's very different to a statue.
yes, that's
Yeah, but light's already fast. Move us. Move our
Exactly,
spaceships.
yes.
So anything that has mass, the problem is as it gets closer to the speed of light, its mass it becomes much more difficult to reach that higher speeds because it's as if it's becoming more massive.
Yeah, it takes more and more energy to get the
to get-
same amount of acceleration.
But is there something, so let's say we had infinite energy and could move faster. Is there something in the nature of mass that breaks up, that's destroyed when it moves at those speeds? Or is it just the capacity to accelerate?
So it's the fact that it becomes more massive just means that you need to put more and more energy to get it faster and faster.
So it's an infinite loop
Yeah,
of going back.
From the perspective of the spaceship trying to reach the speed of light, from their perspective, they're fine. Like they can keep accelerating, and they don't feel that their own mass or anything has changed. They feel just that the universe is zipping by at close to the speed of light. The advantage it gives you is that we have some other things that change. For example, the rate of clocks changes, and so if you're traveling at close to the speed of light, you can. Well, the rate of clocks changes. Maybe the best way is that lengths change. So if you see something zipping past at close to the speed of light, it appears shortened by some crazy. If you have a blackboard, I can show you.
Yeah.
But a watch that's ticking, like a manual wind watch that's ticking at a mechanical pace, that mechanical pace is altered?
It is.
Yeah.
From the perspective of someone watching you move at that speed. And it's all symmetric. So if you're watching the universe zip past you at nearly the speed of light, because you're actually traveling at the speed of light, you see the universe foreshortened, which actually gets you to your destination sooner according to your watch. And so this might be the way we have space travel within human lifespans, is that if you can travel at close to the speed of light, you can reach a distant star within a lifespan. In fact, you could reach a distant galaxy within your lifespan. A galaxy that could be, hundreds of millions of light years away. The problem is, by the time you got back home,
Right.
those hundreds of millions of years will have actually passed.
Yeah.
But
When the Starfleet Enterprise leaves the shipyard and comes back,
right.
they have left.
So they have warp speed,
Right.
and that's another
thing. Yeah.
Yeah. So that's all about taking the fabric of space
Yes.
and
So you actually shrink the space.
You shrink the distance.
Distances, exactly.
Of space.
Yeah. And actually,
Let's do that. That sounds better.
there's a theory proposal now which claims that you can take a bubble and shrink space in front and expand space in the back,
Yeah.
and then that should allow you to do it.
Yeah.
But the problem with that is to do that you need a huge amount of energy, I think.
Yeah, you need
so-
two things. This is the Alcubierre
Yes,
warp drive.
yeah, exactly.
And
This is how the Orville travels, the spaceship on the Orville
Perfect.
travels.
Yeah.
Like,
so the current minimum estimate is you would need the rest mass of the planet Jupiter
Yeah,
to
converted to.
to create one of these Alcubierre warp fields. The other thing is that mass would have to be in this exotic negative mass matter. So a type of matter that has negative mass, which, as far as we know, doesn't exist. And so you can do this in different ways. You can build a warp field. You can make a wormhole. Or there are warp highways I've seen
That
proposals
starts-
for. Every single one of those proposals requires negative mass matter, or exotic matter to do it.
which we don't have.
Which probably is impossible.
So these
never been
energy
observed.
sources are wholly fictional. Question mark. Are these energy sources wholly fictional? Exotic matter, negative mass.
I mean, they exist in mathematics. You can
Yes,
describe them
mathematically.
mathematically.
But
Not helping me get to Poughkeepsie on time.
Yeah. Damn math. Yeah. I mean, not everything that exists in our mathematics exists in reality.
Tragically,
Yes.
this is all we have time for.
Well, it's just fun.
that's great. It's been
So-
fun.